Okay, so let's remind ourselves what we were talking about last week. So mobile transport layer. So what does the transport layer do? The transport layer is in charge of end-to-end connections. So in particular, the property of the transport layer that we're most interested in from the perspective of mobile is the fact that it governs flow control. So we established that the TCP protocol, the way in which TCP organizes its flow control assumes that if a packet is lost, that packet is lost due to congestion and not due to noise. That's not really compatible with mobile communications because as we've established, you can have fading, temporary fading that'll drop the signal, and you'll lose the odd packet, and so there has to be some way of dealing with that. So last time we looked at 3 protocols: indirect TCP, snooping TCP, and mobile TCP that were ways around that. So what I'd like to do now is I'd like to actually, we just discussed what those algorithms or what those protocols did. What I'd like to do now is actually show you some examples illustrating why this is an important principle. So, analysis. We're going to make some simplifying assumptions. So much like the case when we had our analysis of packet loss in mobile IP, we're going to make some simplifying assumptions to make this a little easier to deal with. So for one thing, we're going to assume something called cumulative acknowledgement. So there was a question from a couple classes ago when we were wondering whether TCP acknowledged all the packets at the end or if there was a sliding window. The answer is actually both. Cumulative acknowledgement is the simpler of the two, and that acknowledges all the packets arriving at the end. The alternative to that is selective acknowledgement, but it's a guarantee that all TCP devices can do cumulative acknowledgement, whereas it's not a guarantee that they can all do selective acknowledgement. So we'll just assume that at the end, the end point is when all of the packets are acknowledged. So in other words, if the window size is 5, you send 5 packets, wait for the acknowledgement, send another 5, wait for the acknowledgement, and so on. So a consequence of that is that an entire window is lost if the acknowledgement fails. So if we have one acknowledgement for an entire window, and there's some problem with that window, in other words, one of those packets doesn't arrive, it turns out that the acknowledgement is not sophisticated enough to pick out which one of those packets didn't arrive. It's just everything is lost, and all of those packets need to be retransmitted. So this is kind of a worst case assumption. Another thing we're going to assume for the sake of simplification is that round trip time is much greater than segment length. Segment, that's the same as packet. I think last time I was using the word packet a lot. Turns out segment is probably better when you're talking about the transport layer. And we're also going to assume, so what does this mean? That basically means the amount of time spent waiting for an acknowledgement is roughly the same no matter how many packets are sent. Because if the round trip time is much greater than the segment length, then the total time you spend waiting is the amount of time sending all your segments, so let's say there are 10 segments, plus the round trip time to wait for the acknowledgement, because we're using cumulative acknowledgement. So here's what you do. You send your data.
round trip time is much smaller.
No, round trip time is much greater. So in other words, I'm saying round trip time is the dominant waiting time. So in other words, if you send, let's say, 10 packets, and so on, in this case, the total amount of time you wait is there. It's the amount of time you spend sending your data plus the round trip time. So this is data. This is round trip. So if the round trip time is much greater than the segment length, it would look something like this. Here's your data time. Here's your data time. And here's your round trip time. So the round trip time dominates the waiting time. So this might be the case in if the data was sent very quickly, or if you had very long propagation delays, such as if this was a satellite link or something like that. The reason why this is simplifying is because it doesn't matter how many segments I send, the total waiting time is roughly the same. And we are also going to assume, for simplicity, that the TCP timeout is approximately equal to the round trip time. So in other words, what the consequence of that assumption is that basically we assume that there's not a lot of jitter in this network. We know almost exactly when to expect that acknowledgement to come back, and if it doesn't come back, there's no point in waiting any extra time because it's never going to arrive. Here, I could make this slightly more complicated and still make it valid in the analysis. Basically, all I want is I want TCP timeout to be a multiple of the round trip time. That would also be okay. But for absolute simplicity, let's just keep it roughly equal to the round trip time. Okay, so basically, this will be what this will look like if I just redraw that a little bit. So my congestion window, let's say I have 5 packets. 1, 2, 3, 4, 5. These are all sent. It's a fairly long round trip time. And then the last one is acknowledged. And then I send another 5. The last one is acknowledged, and so on. So this is the effect of the cumulative acknowledgement, which is that I don't acknowledge each packet, and as a result, I don't try to resend. I don't try to resend immediately once I receive the intermediate acknowledgments. In other words, this is always idle timing here. Okay, so the point of congestion control is to avoid blowing the buffer at a downstream router. So again, I'm going to make another simplifying assumption. So we'll assume the capacity of the downstream link is k packets per round trip time. Okay, so now we see the significance of my assumption that the round trip time is much greater than the segment length. If the round trip time is much greater than the segment length, what that allows me to do is it allows me to quantize time by round trip time. In other words, there's not a lot of there's very little difference depending on how many segments I send. So basically, I can organize time by round trip